Hello viewers, in this video we will see the solution to week 7 assignment 7 for the course Principles of Communication Systems 1. First question, consider a band limited signal sampled at a rate greater than Nyquist rate. The original signal can be reconstructed from the samples via interpolation using, so we will see the solution. So reconstruction of original signal can be done using sync interpolation. So answer is sync pulse. Second one, consider the sinusoidal signal cos 2000 pi t. So it is sampled using an impulse train with a sampling frequency fs 1.8 kHz followed by low pass filtering with an ideal low pass filter of cutoff frequency 2 kHz. What are the frequencies of the sinusoids present in the resulting signal? So resulting signal we will see now. Okay, so this is now what they are, so let us see here what is the given thing is cos 2000 pi t. So let us try to find what is the frequency of this signal. So 2 pi fm is equal to 2000 pi, therefore fm is equal to 1000, that is the frequency of this signal is 1000. So the spectrum I have shown here for the message given message signal. So fm equal to 1000 here, it is minus 1000 here. This is the spectrum of the message signal, and the spectrum of the sample signal. So 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 this is the spectrum of the sample signal. So I'll explain you one by one. So here we have, this is a 0, I forgot to include 0 here. Here it is 0. So here it is fm, here it is minus fm. So we know what is fm. Fm is 1k, this is minus 1k. Next what we'll consider here is, this is the message signal. So this diagram is spectrum of the sample signal. This diagram is the spectrum of the sample signal. So after sampling, the spectrum looks like this. So there will be the message signal will be reproduced in the spectrum. So that is what is minus fm and plus fm, which is equal to 1 kilohertz here. And coming to the next, fs, 2fs, 3fs are sampling rate. These are we know that it is fs is the sampling rate. Here this side, negative side, minus fs, 2fs, so on. It will be infinity towards the negative side and towards the positive side. So at every fs, fs, 2fs, 3fs, there will be the spectrum shifted. The message spectrum, this spectrum is shifted at the fs, at 2fs, at 3fs, similarly minus fs, minus 2fs, so on. Now we will only consider the spectrum shifted by fs, which message spectrum shifted by fs. So there are two vertical lines at the fs. At the fs there are we have two vertical lines. One is fs plus fm, and that is 1.8 plus 1. What is this 1.8? fs equal to 1.8, fm equal to 1. This is equal to 2.8 kilohertz. So this line, this frequency is 2.8 kilohertz. And what about this frequency? Another frequency here, this line. So this line, this is fs minus fm, 1.8 minus 1, which is 0.8 kilohertz. So there are two lines here, this line and this line. That line is fc plus fm, and this line is fc minus fm. Now we'll try to draw. Similarly we have negative side. So now this dotted rectangle shows the frequency response of an ideal low pass filter. So what that is the passband of low pass filter, this one, or you can say transfer function. So whatever frequency lies within the passband, they have given fc. Fc is the cutoff frequency of low pass filter, fc, which is equal to 2 kHz. So remember, you can kindly note here, fc is greater than fs. Fc is greater than fs. Fs is 1.8, fc is 2. So fc is here. So this is the passband of the low pass filter. Now this low pass filter has two frequency components. One is this frequency component fc minus fm, which is equal to 0.8. So another is fm, which is nothing but 1 kilohertz. So therefore the output frequencies are 0.8 kilohertz and 1 kilohertz. So 0.8 1 kilohertz and 0.8 kilohertz only. Option C. Option C. Okay, next coming to the next one. Consider the signal. Consider the signal m of t equal to sine 300 pi t. What is the minimum sampling frequency required for no distortion? So we will see this one. Third one. Third one is very simple. So they have given a sine function. So we will try to find what is the frequency. Frequency is 2 pi fm equal to 300 pi, fm equal to 150. This is the frequency of the given signal. So Nyquist rate says that fs equal to 2 fm. This is the minimum sampling rate. Fs equal to 2 fm. So this is equal to 2 into 150 is 300 hertz. So 300 hertz. Option D. 300 hertz. Fourth one. So this one, this is a sinc function. Sine 200 pi t is a sinc function. We will try to find the answer for that one. So 15 sine 200 pi t. So it's a sinc function. So it will have a bandwidth. Fourier transform of this function will be a rectangular function with bandwidth equal to 100. W equal to 100. So therefore, what we will get is Fs equal to 2 times bandwidth. This is 200. 200. Option A. What is this one? This is, we know it's a Nyquist rate. This is the Nyquist rate. So what is Nyquist rate? Fs is equal to 2 fm. Nyquist rate. And sixth one, consider the phase modulated signal. This is a phase modulated signal. The modulation index of the signal. So modulation index of the signal. So modulation index of the signal is kpam. So that is the modulation index. kpam. This is for phase modulation. Remember, it is for phase modulation. Okay. Seventh one, consider FM signal with the carrier frequency of C, modulation index beta, and AM is cos 2 pi fmt. The instantaneous frequency of the signal is, we will see the instantaneous frequency. So definition for instantaneous frequency is Fc plus Kf m of t. So they have given what is m of t. M of t is am cos 2 pi fmt. Am, so it is am cos 2 pi fmt. They have given, and Kf am is delta f, and we know the relationship between beta and delta f. So delta f equal to beta fm. Substitute for delta f. So Fc plus beta fm cos 2 pi fm. So that is option C. Fc plus beta fm cos 2 pi fmt. Eighth one, consider a parallel resonant LC circuit L equal to 1 millihenries and C capacitance C is equal to 50 microfarad. So m of t is very small. M of t is small. You can neglect this part. This is 0. This becomes 0 for this condition. So this is simply a fixed constant 50 microfarad. So we will try to find what is that one. So the frequency of the carrier or Fc. This is Fc or F naught. So 1 divided by 2 pi root LC. L is 1 milli, 1 into 10 power minus 3, 50 micro. So compute this one. It will be 711.76 hertz. So this is option A. Ninth one. So consider the signal m of t equal to 10 sinc pi t. The sinc function. So sinc function again similar to that one. So for the sinc function, this is the spectrum which is equal to W, which is equal to W. So what is W? The sinc to W. So sinc pi t, which is this pi t is equal to 2W. We have to find what is W. W is equal to 5 by 2, which is equal to 2.5. So therefore, according to Nyquist rate, Fs equal to 2 times 2.5 is equal to 5 hertz. 5 hertz. This one. 5 hertz. Last one, what is the minimum sampling rate required to avoid aliasing for this signal? This is little complicated. Anyhow, we will try do it that one. So first we will consider sinc pi t into sinc pi t. So multiplication in time domain becomes convolution in frequency domain. So this is actually a rectangular pulse which we have shown. This is rectangular pulse. So which is having W here. So therefore you can see here the same you have considered here, same W is 2.5. So what will happen is convolution of this operation is bandwidth is doubled, bandwidth is doubled. So therefore 2W, W is nothing but 2.5, W is 2.5. So therefore it is 5 hertz. Similarly for another pair, so you will get bandwidth is 5 hertz by hertz. Now let me call this as function F2, let me call this as function F1. So again multiply these two, that will give you sync fourth power. Okay, so therefore what will happen, the bandwidth will again be doubled, that is 5 hertz plus 5 hertz becomes 10 hertz. This is the bandwidth of the signal, but what is the sampling rate? Twice the bandwidth of the signal, 2 into 10, which is equal to 20 hertz. 20 hertz. Thank you viewers.